This is the Patreon only release of the repair for my Philips AC7900 AM Stereo car player. There is going to be a free release, which is going to be a really condensed version of this. So you guys are going to see everything that I had to go through to fix this thing. And that's coming right up here for my Patreon subscribers. Thanks for watching. Check out this old radio here. This is an old Philips radio that actually was in an old car that I had at one time. And this was I guess this was probably an aftermarket radio. It's a Philips. And anyway, I kept the radio and I scrapped the car because I felt the radio was probably more valuable than the car. Check this out. It is AM stereo. It's an AM stereo radio. It only receives signals on the Motorola Sequam system, which just happens to be the type of little AM transmitter that I built. So we have it receiving the signal, although the right channel is very low compared to the left channel. If I turn it on here, now it's only on AM. If I go to FM, I'll get blasted out of here. Right. I have to have the balance control almost to the right, but you can hear the separation. So maybe we'll take this thing apart and see if I can get that level up on the AM demodulator, see if I can get the level balanced. Be kind of a cool little thing to have. It's just another one. I remember that I had this thing. I thought this radio got tossed years ago. I do remember pulling it out of the old Mustang that I had at one time. Actually, I think it was my wife had this car. And somebody had put this radio in. I think their car originally had an AM radio, and they put this radio in. That was back in the day when AM stereo was the big thing around town. Although the rock and roll station was actually in the con system, so this radio wouldn't receive stereo on this channel. Well, the one channel that we used to listen to. There was two channels here in the Vancouver market back in the 80s, and one was 730, which was using the con system, and the other one was 1040 kicks. In fact, I've still got one of their stickers because back in about I'm going to say it was probably 1986 or so, I remember that they, contests, right? And, I won a contest with them. And it was, you had to answer the phone and you had to say 1040 kicks. That was all. If you said that when you answered the phone, you won money. And you never knew when they were going to call, because how these radio stations worked was, they would say they're going to call someone, but they had actually already made the call. That was all recorded in advance. So when they'd say, okay, we're going to call somebody now, sit by your phone. Well, I could just see all these people just sitting by their phone waiting for the phone to ring. And I knew that they usually did it at the lunch in the noon hour. They usually made the call. And at the time, I used to go home for lunch. I was working at the TV shop at the time. And I'd go home for lunch because I was only a block or so away. I had a little apartment about a block away from the shop that I worked at. I remember going home, and the phone was ringing as I got in the door. It was just probably like 5 after 12. And I heard the phone ringing, and instinctively I picked up the phone and it said 1040 kicks, and the guy was on the other end of the phone all jacked up, right? You won. It was like $1,000, I think it was $1,040 if I remember correctly. But then I had to actually go down and claim it in person. But I couldn't go down and claim it in person because I was working during those hours, and my boss wouldn't let me have the time off. So I remember getting my wife, which I wasn't married to her at the time, but we were certainly living together. I remember I had to give her my driver's license, and so that she could go down and claim my prize for me. And she came home with an envelope, and we opened it up, and it had some $100 bills stuffed in it. It was kind of cool. Only time I ever won anything off a radio station was that. And the guys at work wouldn't believe me. When I went back to work, the guys at work wouldn't believe that I had won anything. So we're going to pop this thing apart. I'm just going to shut off this noisy power supply because that thing, the fan in that thing makes enough noise to wake the dead. It's really quite annoying if you You know, I mean, it probably comes through on camera very loud too, but the fan in that thing is quite loud. I'm not one that works on car stereos, so I have no idea how this thing even opens up. I'm imagining if I take out a couple screws, the top should pop off. Okay, there's the bottom. Actually, I remember modifying this thing many years ago to remove the ceramic filter, which limits the bandwidth for AM to give it more high fidelity sound. I'll show you that because I'm going to rework that in this video, but I won't be doing that in the free version. So you guys can see it. One thing that I never worked on was car audio. The shop that I worked for, that was the one thing that we refused to work on, was car audio. I never worked on it before, and I don't want to get into working on it now. But I'm just curious as to whether I can see where the stereo decoder is in this thing. I have no idea. I've never looked into one of these things before, so I really have no idea what I'm looking at in this thing. Okay, I see a 455 kilohertz filter down here. That's got to be the AM section. Looks like the 455 kilohertz filter was jumpered. I think I did that at one time. That was to improve the fidelity. I turned it from a narrowband receiver into a wideband receiver to get the sound. I think I did that. Okay. I'm going to guess that this is probably the decoder chip down here just because it's a Motorola chip. So I think that that's probably the AM stereo decoder. See this Motorola chip down here? What's the number on that thing? It's an MC13020. Let's look that up and see what it is. So, as I thought, the MC13020, as you can see here, is a Motorola Sequam AM stereo decoder. It's a silicon monolithic integrated circuit. Here's our pinout. I actually got 6 pages of documentation on this thing, so we can actually scope this thing and see whether we're getting a signal level, a balanced signal level coming out, or whether it's something in the chip that's low. But here's our specifications. It's got 30 dB signal separation, which is pretty normal for AM stereo. It wasn't known for having a lot of separation between the channels, but it's still, the sound is actually pretty good on AM stereo. So here's our input. It takes your IF input from your, and actually I think it takes it right from the IF. It doesn't even take it from the decoder. It does the envelope detection internal. So that's the difference between a regular mono radio, which just used a germanium diode to detect your audio from your carrier. In the case of the AM stereo, it actually takes the IF input right from the ceramic filter. So this is going to the ceramic filter here, and it does your detection. So it's got your envelope detector for your monaural signal, which passes through here, the left plus right signal, over to the matrix, and then it's got your variable gain amplifier, and then you've got your phase detector here, your error amp. There's an oscillator here, divide by 8 oscillator. This way you detect your I and your Q for your phase detection to deliver your left minus right signal. Your pilot decoder here, this is what turns on and off the stereo to determine whether it is a stereo signal, and you can force it to mono by I think it's bringing it low or high. It showed me here on one of these. Here we go, on this side here. If you force pin number 9 low, pin number 9 is normally pulled up to VCC through a 100K resistor here. So it's pulled up to your 8 volts. So you pull it low and it will force mono. But what we're interested in here is we're interested in the pinout here, because obviously this doesn't really mean a lot. This is your block diagram that shows you what's actually going on. There's a fair bit of circuitry inside here. There's a lot going on to decode that signal. Here's your switching here for mono stereo, and then the matrix. So the left minus right signal, it The composite signal comes in through here. One side goes through and is decoded as the left plus right, or the mono signal here. And then the secondary signal comes in, and it goes in through your I and Q detectors. And the I detector, it will detect an error and use that to control the gain. Then it comes through the Q detector, through the AGC, through some external circuitry here, through the pilot decoder. It also follows its way along here. Your left minus right signal is decoded here. So you have your left minus right signal and your left plus right signal. The switch, all the switch does is it just turns this signal on and off. So if it's a mono signal, or if it's a signal where you've forced it to mono using the switch here, this will just shut that signal off. So once it allows the signal to proceed through to the matrix, then it's going to be subtracted from the left plus right, and you'll get your left and right audio outputs. Basically, I think. So if we look at the introduction here, here's Motorola's explanation. In CQAM, conventional quadrature amplitude modulation has been modified by multiplexing each axis by your cosine 0 as shown in figures 2 and 3. I guess we have to look at figures 2 and 3. Yeah, it's figures 5. Where's figures 2 and 3? Must be on this side. Here we go. Here we go. So here's what they're doing. There's a fair bit of math involved here, but the amplitude is not a correct sum signal for each envelope because they're modifying it, right? They're changing the angle of the modulation. And that's the difference between pure phase modulation that was used in the Magnavox system and the Harris system. The Harris system was, if I remember correctly, the Harris system was a fixed angle. The Harris, Magnavox, and Motorola systems are all very similar. They use a phase modulation of the actual carrier. The amplitude modulation is the sum signal, or the left plus right, and the difference signal used a phase modulation of the carrier. The big differences between the three systems were, and I may be incorrect here because it's been a long time since I've read up on it, but I believe it was the Harris system was a fixed angle and the Magnavox system was a variable angle. And those two systems actually provided a little better separation, but the problem with those systems is they caused severe distortion when you were listening to the broadcast on a conventional AM radio. So Motorola, through their engineering of they call it their compatible, CQAM, compatible quadrature AM modulation, that's what CQAM stands for, is they did it by varying the actual angle of the phase modulation based on the loudness of the signal. So a signal that was loud had, I think it was less separation than a signal that was weak, if I'm not mistaken. Let's just see if it says here. But anyway, it's been modified by multiplying each axis by the cosine of 0, or O as they call it here, a little mark here. It's shown in figure number 2. Here we go. Right? And so the amplitude is not correct sum for the signal envelope detection. But the envelope is now compatible with existing monaural receivers by the way that they do it. So this is your basic QAM, basic QAM. This would have been, I think this was the Magnavox system here. But they use this formula here for your average carrier, and because it caused excessive distortion, Motorola modified theirs to change the angle of the receiver of the actual carrier, and they did theirs the way that the conventional was. It was the square root of 1 plus the left plus the right squared plus the left minus the right squared in the envelope. And the way that Motorola did it was the 1 plus the left plus right over the cosine of 1 plus left plus right. So in other words, they changed the amplitude, or not the amplitude, they changed the phase of the carrier depending on the envelope, of the amplitude of the envelope. Anyway, and that's what they say here. And conventional quadrature, see this stuff here that you're seeing here, this is going to go on the Patreon only release. So this, I'm boring you guys with the details by reading you what's on the documentation here, because even this is complex. I don't even fully understand this. I never really studied AM stereo. I just listened to it. So this is actually the first time I've even seen these documents. But in conventional quadrature AM modulation, they modified it by multiplexing each axis by the cosine as shown, and resulting in a carrier envelope that is 1 plus left plus right, i.e. the correct sum signal for monaural receiver and stereo receiver operation in monaural mode. 25 Hz pilot is added to the left plus right information at, or the left minus right information at a 4% modulation level. That's how the chip detects it. The MC13020 13020P takes the output of the IF amplifier and performs the complete CQAM decoding function in the absence of a good stereo signal, produces an undegraded monaural output. Note that in figure 4, the left plus right information is delivered to the output always comes from the envelope detector. So where is figure number 4? That would be figure 3. This must be figure 4 here. Yeah, here's figure 4 of the block diagram. And it decodes the stereo information by first converting the CQAM signal into a QAM signal and then detecting the QAM signal. So it converts it from the compatible QAM to a regular quadrature amplitude modulation. The conversion is accomplished by comparing the output of the envelope detector and the I detector with the error amplifier, and that's here, right? And this is where your variable gain comes into effect. This provides a 1 over cosine correction factor, which is then multiplied by the CQAM incoming signal in the variable gain block. There you go. Thus, the output of the variable gain block is a QAM signal, which can then be synchronously detected by conventional means. So basically what they're saying is they are converting the compatible, or the variable angle phase modulation into a fixed angle, into conventional quadrature modulation by changing the gain here and detecting it. And then the I and Q detectors are then held at 0 and 90 degrees respectively. So because in quadrature modulation you've got two carriers that are out of phase by 90 degrees, right, with each other. So now you can work on those. And it's a reference signal from the phase lock loop divided down VCO. So here's your phase lock loop here. So this is where you generate your demodulation signal. The output of the I detection is 1 plus left plus right, with the added benefit of the over envelope detection being able to produce a negative output on strong co-channel or noise interference. This is used to tell the lock circuit to go to monaural operation. And the output of the Q detector is the left minus right and the pilot information. So the Q detector here has got your pilot and your left minus right information on it. The VCO here operates at 8 times the IF input frequency, which ensures that it is out of band even when a 260 kilohertz IF frequency is used. But typically you use 450 kilohertz. But this way it allows it, even if the radio design were to use a 260 kilohertz IF, it would still work. It would be out of band. But most radios are going to use 450 kilohertz IF. That's your standard, frequency that's used with synthesized front ends. This places a VCO at 3.6 megahertz, which permits an economical crystal and ceramic resonator. So it's easy just to get cheap crystals if you're using 3.6 megahertz. Crystal and VCO is very stable, but cannot be pulled very far to follow front end mistuning. Pulling capacity is 100 hertz at 450 kilohertz, and DQing with a resistor can increase the range only slightly. Therefore, a crystal approach can only be used with very accurate, stable front ends. By comparison, a ceramic and an LC VCO circuit offer a pull-in range of at least or the order of 2.5 kilohertz at 450 kilohertz. So ceramics are accurate enough to avoid trimming adjustments and can be attained with matching capacitors. So that's why this would use a ceramic filter. Here we go, the other side here. Again, this is for the Patreon release only. In the PLL filter circuit, pin 19C1 is the primary factor in setting loop corner frequency of 8 to 10 hertz in a lock. Internally controlled fast pull-in is provided. R2 is selected to slightly overdamp the control loop, and C2 prevents high frequency instability. The level detector block senses carrier level and produces an optional tuner AGC source. It also operates on the Q AGC block to provide a constant amplitude of 25 Hz pilot at pin number 11 and delivers information to the pilot decoder. And then your pilot and co-channel filters, your Q AGC output drives a low-pass filter made up of 400 ohms internal and 430 ohms and 5 microfarads external. From this point, an active 25 Hz bandpass filter is coupled to the pilot decoder. Pin 14 is another low-pass filter that connects to the co-channel input. Pin 12 is a 2-to-1 reduction of the 25 Hz pilot to the pilot decode circuit, which will cause the system to go monaural when components shown, referring to figure 8. Here we go. This is your active bandpass filter here. And it says the co-channel input of pin 12 can be adjusted by changing the external 1.5K resistors. The value shown will set the trip level at about 7% modulation. And the pilot decoder has 2 modes of operation. When signal conditions are good, the decoder will switch to stereo after 7 consecutive cycles of the 25 Hz pilot tone. When the signal conditions are bad, the detected interference changes the pilot counter so that it requires 37 consecutive cycles of pilot to go to stereo. In a frequency synthesized radio, the logic that mutes the audio when tuning can be connected to pin number 9. When the pin number 9 is held low, it holds the decoder in monaural mode and switches it to the short count. The pin should be held low until the synthesizer and decoder have locked onto a new station. The 300 millisecond delay should be sufficient. If the synthesizer logic does not provide sufficient delay, the circuit shown in figure 9 may be added. So we can add that circuit there if it's not enough time. And it says once pin 9 goes high, the pilot decoder starts counting. If no pilot is detected for 7 consecutive counts, it is assumed to be a good monaural station, and the decoder is switched to the long count. This reduces the possibility of the false stereo triggering due to signal level fluctuations of noise. And the phase lock loop goes out. If the phase lock loop goes out of lock or interference is detected, the code channel protection circuit, before the 7 cycles are counted, the decoder goes into long count mode. Each disturbance will reset the counter to 0. The level detection will keep the decoder from going into stereo if the IF level drops 10 dB, but will not change the operation of the pilot counter. Once the decoder has gone into stereo mode, it will instantly go back to monaural if either lock detector on pin 10 goes low or if the carrier drops below preset threshold. 7 consecutive counts of no pilot will also put the decoder into monaural. In stereo, the co-channel input is disabled, and co-channel and other noise is detected by the negative exertion of the eye detector as mentioned before. When these exertions reach a level of approximately 20% modulation of co-channel, the lock detector puts the system in monaural, and even though the PLL may still be active, the higher level of co-channel tolerance provides a hysteresis to prevent chattering in and out of stereo with marginal signals. So when all inputs to the pilot block are correct and has completed its count, it turns on the stereo, sending to the L minus right to the matrix and switches the pilot lamp pin to low impedance to ground. In summary, it should be noted that in CQAM, with both channels AM modulated, the noise increases in stereo at 3 dB less on program material. Therefore, it is not a major concern in the choice of monaural to stereo switching point as it was in FM, and blend is not needed. So here's our pin descriptions. Pin 1 and 2 is your detector filters. Pin 3 is your IF signal. Pin 4 is your level detector. Got that here. 5 is your error amp. 6 is your voltage source, 6 to 10 volts DC. 7 and 8 are your left and right outputs, NPN emitter followers. Pin 9 is force monaural. 10 is your lock detector. 11 is your AGC for your Q output. And it's emitter follower, NPN emitter follower with 400 ohms from the emitter to pin 11. Pin 12 is your co-channel input, a 2K series resistor in and 47K feedback. Pin 13 pilot filter input to the op amp. Pin 14 pilot decoder input on an op amp output emitter follower. Pin 15 stereo amp, open collector of an NPN common emitter stage and can sync 50 milliamps. Pin 16 is ground. Pin 17 is your oscillator input. It says do not connect pin 18 to ground, or do not connect to pin 18 or ground. Pin 18 is your oscillator feedback. It's an NPN emitter follower. Pin 19 is your phase detector output, and pin 20 is your detector filter. That's the boring stuff from this chip. Let's do some measurements of this thing and see if my levels are correct coming out of the chip when receiving an AM stereo signal. I know that my stereo transmitter, the levels are balanced because I've confirmed it on my boombox, and the levels are the same for both the left and right channel. So to clear that up, we know that that is correct. It is this radio that is not correct. Okay, I'm scoping pin 7 now, which is the left output. If we look over at Mr. Scope over here, we'll see that the level is looking pretty good. Getting a bit of noise there when I move things around. And we'll go to the next pin. And here's the right output. So we know that the level coming out of the IC is actually good. So why is it so bad going to the speakers? I switch it to mono. There, now it's in mono. It goes to a couple capacitors here. It must be, it's going to have to be, it's going to be in the switching beyond this because my level is, that's just me. Just my connection to ground here from my probe. It's causing all that noise. But pin 7 and pin 8 here are the same. The levels are the same for both. So we know that the AM decoder is good. So let's just trace for where it goes from here. It's obviously going to go to, it might even be a mechanical switch, you know that. And FM is good on both sides. This is going to a mechanical switch, I think, on this receiver. Let's just turn this thing over here. Okay. I don't want my power supply to short out, that's for sure. I think we're going to find it's going to come up on one of these pins here, and it's going to go up to a mechanical switch in the front end here. So my output is there. That's one, and that's the other one there. And it goes through these capacitors. And it's the same on both of these. We'll just follow the circuitry and see where it goes. Okay, the capacitors here, it goes up to this point here. That's the same here. It goes down. Where does it go? It's right in here where I'm losing my signal. Higher signal there, and this is the lower signal right there. What is in this area right here? Oh connection right here. Right there. There it is. Right there. There's a crack solder connection right there. Right there. See it? I don't know if the camera's going to pick that up or not, if I can go in any closer without it going out of focus, but I just found the problem with this radio. By going through with the scope, that connection right there has a crack on it. You can see it moving. Let's solder it up. Shut off the power here, and we'll fix that connection, and then this radio will be fixed. Ah, crap. Let it free solder. Ah, how did I grab that? Try some real stuff. Better. We'll just put some fresh tin on my soldering iron here. Hopefully it'll last a little longer. Okay, shall we try it now? Turn the power back on. Tune in my station. Pushed the wrong button there. I bet you if I take this one here off, I bet you if I unsolder this, it'll go to narrowband and it'll sound like crap, because I remember putting a jumper in there over that filter to I remember putting a jumper in there to filter out the or to bypass the. I hit the wrong button there. See, I can tune this off frequency. Come on. Still coming in, but it really made a difference in terms of the sound quality. If I shut it off, and we'll just remove this little jumper that I put in just for the heck of it. I'm going to put it back in though because I want the good sound, but we'll just remove this little jumper that I put in here a long time ago. Okay, now it'll sound like a regular AM radio, like crap. Now I'll go off frequency or go off center. Now it sounds like regular AM. And if I bridge that, listen to the highs come up. See? AM sound, and there's hi-fi sound. What would you rather listen to? Narrowband AM or wideband? See, Sony always had a little switch on theirs, but this one didn't have a switch, and I remember doing that years ago on this radio. I was looking for better sound, and I bypassed the ceramic filter. Now I'm thinking, this radio is never going to go back in use in a car again, but it might be nice for DXing AM stereo. And because car radios are typically fairly sensitive. So I'm thinking I might like the narrowband option. And I'm thinking maybe one of these switches on the front, like the one that selects metal tape or DNR. One of these switches could be rewired just to jumper that. I'm going to do that. Let's just see which switch goes where first of all. I'll shut off the power so I don't blow anything up here. We'll just take a quick look at the switches on the front here and see which switch does what. And rewire that little jumper so that I can switch this thing between wideband and narrowband. Might even be worth it to see if the cassette works on this thing. Okay, here's some little switches down here. One of these switches I'm sure I can use. One is a momentary switch. This one here is a push switch. Metal. I wonder. Yeah, you know what? I'll never play a metal tape on this. I don't own any metal tapes, and I like the sound of them better in the non-metal mode anyway. So I'm going to wire this thing up. Just find out which one of these wires goes to this switch. And we'll use that switch to bypass the ceramic filter. It looks like it might be the blue and the white wire right down here actually. Let me just grab my meter and see whether that switches when I press the switch in. White and blue. Nope. I am in continuity mode. Let's just see which one of these ones actually does go to that switch. One of these wires here. Could be these wires here. Oh, you know what? What are these going to? It might be these wires. I may have already done that before and then wired it permanently wideband. I forget. There's a couple wires that have been, looks like they've been added onto the switch here. I wonder if they are, I wonder if these are going to this switch. Looks like they might be. It looks like this switch might be, it might have been used at one point to bypass that, and for some reason I took it out. Maybe the switch wasn't working. Let's just take a look and see, because it kind of looks like these little wires here are going right to that switch. And they're not going anywhere else. Let's just see whether that is what I think it is. I think these are going to the switch. Aha! That's exactly what they are. Those wires go to the switch here. So I just have to extend a couple of wires from there over to here, and I'll have a narrowband, wideband switch on this radio. Very cool. I think at one time I probably did have a narrowband, wideband switch on here, and for some reason I decided just to make it permanently wideband. Can't imagine why I would ever want to do that, but who knows? It's I'm just going to use a couple pieces of regular Cat 5 wire. The same color at that, just whatever I have on hand, right? So say this radio is never going back into service, I just want to play around with it. Okay, let's looking for some of my small heat shrink tubing. Okay, let's solder these wires on. Ow, 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 ow. Ouch. That hurts when that happens. That really hurts. I just flicked some solder. And where did it go? It just went down between my pant leg and my shoe and into my socks. And 800-degree molten solder. It stings. Especially when you can't get rid of it. It's stuck there till it cools. Put that down there. This one down here. Might help if it's plugged in. There. That'll prevent them from ever shorting out. Let's take the other side of those wires. We'll just move them around here and we'll stick them down to the board here where I had that jumper in place from way back. Okay, shall we try this thing and see how it performs now? Put it back on. There's normal. Should be wideband there. Oh, you know what? That's why I took it out before that switch is shot. I thought one time I had the wideband switch hooked up there. That's what's happened. That switch has gotten dirty and stopped working. That's why I disconnected those wires and put the jumper in. Now I see, now it comes back to me. That switch went bad. Let's see if we can clean that switch and make it work. We'll use some Deoxit D100 in the single shot dispenser. I'm tuned off frequency, that's why. I'm set to 1430. If I go to 1440, of course, I'll hear it. But at 1430, if I'm in wideband mode, I'll hear it. And now the switch is starting to work. Ah. This track doesn't have much in terms of high frequency in it, but if I go off frequency, you can certainly hear it now, right? I'll give it another shot here, cleaner, just to make sure that we get some in there. Now you hear the difference. And for those of you concerned about the bit of hum in my AM transmitted signal, it's, well, first of all, the transmitter is not grounded, that's part of it. But the problem I've got is that my little cheap-ass MP3 player that I'm using is picking up noise. If I unplug the audio inputs from the transmitter, it's quiet. But when I plug in the little MP3 player that I'm using, and I've just got some Music Bakery content streaming on that, just playing for my content, yeah, it's getting a bit of a hum. And if I move the MP3 player around, the hum changes. But it depends on where I am, right? Because when I'm sitting in my office listening to my boombox, there's no noise whatsoever. If I move the MP3 player in relation to the transmitter, it will get hum in it. You know, so I have it kind of minimized so that I don't hear any hum in the music on my boombox. But I'm hearing it in here on this radio a little bit in the background. You hear it in the quiet passages when the AGC comes up. That's when you hear it. When music is playing and the AGC is low, and so that's how I know it's getting into the audio feed. Maybe I'll put some chokes on the audio, the actual feed line. That might eliminate, but definitely that hum that we're hearing is actual RF getting back into the audio line. That's what's causing it. But you hear the difference here. There's AM radio sound, and there's hi-fi AM radio sound. I'm happy. Now I've got this radio back working again, sort of. Well, I guess it is working. I can put it back together and put it back into storage. Put it back into my collection of AM stereo radios. So this makes, what else have I got? I've got two Sony Walkmans. I've got the boombox. I've got car stereo, this car stereo, and I've got an AM tuner. And my AM tuner is not receiving any AM stereo signals, so it's going to have to be repaired. And I'll look at that at some point. We'll fix that when I get it receiving a signal in stereo. I'll do that one fairly soon, I would imagine. But this one's back running. I fixed the low audio problem. There we go. Okay, I put the top on this thing now, and oh, I guess we should check the cassette out. I'm not worried about wires on the bottom shorting. As you can see, there's plastic on here, so that's not going to be an issue with the wire shorting out. We should see if the cassette deck works on this thing. Yeah, here if I move the antenna around, the hum that I hear changes. I wonder if this cassette's working. Let's just try it out and see whether I can trigger this cassette mechanism into loading. How do you load this thing? I want to try and trigger this thing without putting a cassette into it right away because I want to make sure that it's not going to eat. Oh well, let's try cassette. Let's see if it works. Cassette goes in. I believe it works. And if I press this in, it should go the other way. Yes, it does. It works. Auto reverse still works. Irish Rovers. This thing's been sitting since the 80s and it's got the original belts in it. And it still works. Fast forward and rewind. Love it. Good old Philips. There we go. Fully functional again. AM stereo. Let's put the top on this thing and it's done. Thanks for watching.